Our next presenter is Simona Abis.
Yes.
Abis, okay. She will present the changing economics of knowledge production.
Thank you so much for having me today, and in particular, in person, it's great to see many of you again. So today I'm going to present a paper which is joint work with my colleague Laura. So let me jump right into the motivation for this project. In this project, we ask a question which is a pretty simple but a pretty important question. What we ask is whether big data technologies are going to revolutionize the production of knowledge, just like the Industrial Revolution revolutionized the production of physical goods. Now, let me explain what we mean by this with an example. So imagine that we're back in the days, there's a blacksmith and he has a bit of capital, bought some tools, and his own labor produces some goods that then sells into the market. Now imagine that I come and give a lot of capital to this blacksmith. Well, he can potentially scale up production a bit, he can hire a few apprentices, but he cannot scale up that much because the bottleneck is really his own labor. And so the additional value of that capital is not that high. But now imagine the Industrial Revolution happens and I have the owner of the factory. Now we have a technology that allows to scale up production with a lower need for human labor. And so if I was to give that same amount of additional capital to the factory owner, now he could do more with it. He could scale up production by more, and the marginal value of that additional dollar would be higher. Now imagine this parallel. I have an investment manager. This investment manager has a data set with 100 variables, 1 million observations, and he's using what we call old tech analysis, think regression, to draw some insights from this data and get some trading signals to then utilize to trade in the market. Think about trading signals broadly as the knowledge for the investment management industry. Now imagine if I was to give this investment manager 1 million more variables and 10 million more observations. Now, clearly, he cannot plug these million variables into his regression analysis. He can extract a bit more value from this data, but the marginal value of each additional data point is not that high if I don't have a technology that say lever these additional data. Now, imagine that my investment manager instead is endowed with the AI skill, big data technologies. Let's call them AI. Now, when I give him these additional million variables and 10 million observations, just like our factory owner, now he has a tool that allows him to lever this additional quantity of data and extract insights from it. So how we interpret that is that the marginal value of these additional data points is higher when put in the hand of my investment manager, which is endowed with the AI skill, relative to when I give it to my investment manager endowed with the regression skill. The purpose of this paper is to quantify this change. Is this a marginal incremental change, or is this a structural change? And we're really after this quantification. Now, in this paper, obviously, this is very important for a lot of things that we care about, particularly as we observe a rise in AI in a lot of different industries. And answering these questions can have very big implications for employment, labor income share, competition, firm size, and a lot of other things that we care about. In this particular paper, we focus on the investment management industry. That's not to say that our reasoning only is valid there, but we decide to focus in an area where we could do this quantification a little bit better. Why investment management? Is clearly a knowledge industry. We could have picked something else. Another clear knowledge industry is consulting. They got data. You have the consultants, they analyze the data. Their knowledge is what? Advice to firms. The investment managers, they have data, they analyze the data. Their knowledge is what? Trading signals. So it's a clear knowledge industry. Additionally, they're early adopters of AI. This is important as we are still in this transitory period. And third, which is also important, you will see in our paper, is that, well, investment management pays a lot. And so they're going to face less labor market constraints when in a lot of industries we're trying to hire AI people. And so that's why we select this industry. Now, our paper can really be summarized by this flow chart. This is exactly how we think about the production of knowledge. And you see that I put some equations behind this, but if you understand this flow chart, you understand exactly what we're trying to do in here. So we think about the production of knowledge as having two steps. At a first stage, I need to invest in data. How do I produce knowledge? Well, I need data. I need to analyze this data. I need data. I need to invest in collecting it, cleaning it, structuring it, maintaining it, putting it in a database, allowing my analyst to query the database, so on and so forth. This requires investment. This requires labor. When I invest in structuring data, and by the way, I can even purchase a data set externally. I still cannot plug it into a regression or into a model the next day. All of us that do empirical analysis, you know that whenever you acquire a new data set, there is a lot of work involved in just making it ready to then run that analysis. All of that we think about is first stage. Get raw unstructured data, process it, and make it into structured data. What we call broadly data, and the big D in all of my slides that you will see, think about it as structured data. Structured data is the input in my knowledge production function. My knowledge production function has only two inputs, data and analysis labor. Now, where is the big change? The big change is really happening in this analysis portion. We're going to have two different knowledge production functions. My old tech skilled investment manager and my AI skilled investment manager. And what we are going to be after is really quantifying the difference in the parameters that regulate these two different technologies for producing knowledge. We're after quantification, so I'll briefly show you a model that we utilize for measurement, which essentially we put equations behind these two steps. And then we're going to estimate this model structurally utilizing real-world data from the investment management industry in the United States. So let's move to the model. These knowledge production functions, as I said, there are two, one utilizing the old technology and one utilizing the new technology. Broadly, I'm going to call them old tech and AI throughout this presentation. These are classic Cobb-Douglas production functions. So how do I think about them? Well, there's going to be for both technologies a technology-specific productivity parameter, which is time varying. We get better at using AI the more we use it. And that's common to everybody in this industry. We're also going to have some firm-specific productivity parameters. Some firm may be, in general, better at analyzing data with either of the two technologies. And then we have our production inputs. Our production inputs are data and labor. This big D is the same in both of these things. That's not by chance. Data has a very nice property that's different from capital. Data is non-rival. So if I am JP Morgan, I can have some teams that use the old technology, some teams that use the AI technology, and they're both querying the same data set. If I've analyzed some data with the old tech, it doesn't mean that I cannot analyze it with AI as well. So data here is the same stock of data at the firm level, and the firm can choose how much of the different technologies to invest in. The second input in my knowledge production is labor. Labor here is different in these two technologies. Capital L is my AI endowed investment manager. Small l is my old tech endowed investment manager. So firm will invest in structuring data, that's going to give them that capital D, and then they will choose how much to hire of the AI endowed versus old tech endowed analysts. Now, what we're after is these parameters, these exponents, that really regulate the productivity of analyzing big data sets, or the capital of the labor to data ratio, similarly to how we think about the labor to capital ratio the Industrial Revolution, or more classically in goods production. So what we're after is understanding if these alpha and gamma are indeed different from each other, and if so, how much? And that's going to allow us to say whether this is an incremental change or is a structural shift. Now, what I've explained to you is the second box in my flow chart. Now, we still need to talk about the first box. How do I get my capital Ds? Well, the data inputs in my knowledge production is not raw data. They need to be structured, clean, and made machine readable. These require labor, which we call lambda in here, and this labor has diminishing marginal returns. Structured data, which is the stock of data of a firm at a given point in time, is given by the stock of data that I had at the previous point in time, plus the amount of new data that my data managers are able to clean, structure, add to my data set in the current period. Importantly, data depreciates at this rate D. What that means is that some data from 20 years ago, 10 years ago, might be less valuable than the new observation I acquired. New data sets might be more relevant. There can be all sorts of reasons why data does not just stay and have the same value. But you can really think about this data as a new form of capital that we need to invest on to be able to use it for knowledge production. Now, what are firms maximizing? Well, firms are trying to maximize the value they extract from data. What is that? Well, it has how much am I able to produce with the two technologies? As I said, firms can have a mix of the two, data is non-rival, minus the cost that I need to incur to be able to do that. I need to hire and I need to pay the wages of all workers of the three types, my data manager, my AI analyst, and my old tech analysts. Plus, there is this Gordon growth term of the present value of the future value of data. Now, here, I'm going to take three first-order conditions with respect to the three key choice variables of my firms. How many workers of each type do I hire? How many data managers, AI analysts, or old tech analysts? If I take first-order conditions with respect to those three choice variables, what I got are these equations right here that are going to allow me to pin down the exponents of my Cobb-Douglas production functions and the parameter that regulates the decreasing returns to data management labor. I still need to quantify one more thing. I don't observe the data stock of firms. So I need an additional condition that allows me to figure out how much data each firm has at each point in time. That additional condition comes from equating basically a rearranging of my equation 3 right here with the fact that data accumulates over time. So if I rewrite the condition of dt plus 1 is a function of dt, I can go all the way back to assess what data should do based on time 0. And so this is basically a different way of just rewriting this function right here. And so the amount of data that a firm has must be optimal given the wages that I'm paying to the different types of workers, but data also accumulates over time on the basis of that, the discounting that I've showed you earlier. We do not structurally estimate a different DI0 for every firm. We estimate an average DI0 and we map it to all the firms according to their data management hiring at the beginning of our estimation period. Now, we also compute our productivity parameters, and those, if you wish, if you want to think about them from like a regression perspective, think about it as firm and time fixed effects. So we're going to have all of these conditions for each firm for each point in time, and these parameters we're going to get them from averages, either time series averages of all the conditions for a given firm, or cross-sectional averages for all of the firms in a given point in time. Now, what do we need now? We need to structurally estimate this model. What do we need to measure in order to be able to do that? We need to know how many workers of each type, each investment management firm in the US is hiring at every single point in time. We also need to know how much they're paying them. Obviously, that's not commonly available data. So how do we go about measuring this? First, how many workers of each type? Well, we use demand for labor from job postings data, which I'll show you in a second how then we transform into stock of labor. But we start from demand for labor. We acquire the Burning Glass Technologies data from 2010 to 2018, and we filter that data to include predominantly investment management firms. So we subset it to only the jobs that were demanded by investment management firms. Among those jobs, we identify the AI, or tech analyst, and data management jobs. We use here a dictionary-based approach, and I'll tell you in a second why that choice. But before I do that, let me tell you, we utilize the full text of every single job posting to do this categorization, because here we're after a very fine-grained definition. We need to identify analysts of two types. They might have the same job title. This job title might mean something at the beginning of something else later on. And so we really need to base it on the full text and look at the relative frequency of skills of the three types that are mentioned in a given job posting. We do that exercise that allows us to identify all the jobs that are AI or tech or data management, and these are mapped to each investment manager in the US. What I'm showing you here are work plans. Now, what's important that you notice in this word cloud is that each word cloud actually contains every single keyword belonging to the three categories. What you see is the frequency of the words that are mostly mentioned in jobs we categorize as AI or tech or data management. If our model was wrong, you will observe that there would be a predominance of all the words everywhere. But what we see instead is that actually in these jobs, machine learning, AI, data science are way more prominent. Here, statistics and mathematics are way more prominent. And here, data-related skills are way more prominent. The innovation in measurement relative to other papers that utilize this burning glass data are two. First, we focus on investment management firms. We identify those firms by looking at firms that file 13F filings and using a preprint data set. We develop a novel algorithm really tailored at employer name matching, and focusing on a given industry allows us to really be more precise as to which keywords matter exactly in finance that might not matter in other industries. Second, our job categorization. Of course, this dictionary-based approach is more labor and computationally intensive. I'm not even going to start to tell you how many full nights I've spent reading job postings and trying to really figure out what matters in this set. But this really allows us to be very context specific, which is required for our estimation to have such fine grains of labor. And then utilizing the full text of the job postings relative to, let's say, just a structured skill list the Burning Glass provides is extremely important in here because we're really after this fine grain separation. So if a job that's a typical old tech job mentions, well, knowledge of machine learning is a plus, that's not an AI job in our sample. These are some examples from two similar jobs categorized in the three different ways. In the interest of time, I'm just going to move quickly, but one is a quant analyst or tech, lead data scientist, and SQL data analyst. These are the types of jobs that you can think in here. We accumulate these jobs into stock of labor by using information from the Bureau of Labor Statistics. We have a burning period in which we accumulate this series based on the separation rates and the posting to hiring rates at a very specific subcategory level that will match the burning glass data. What that allows us to do is that, well, we utilize a burning period. In this example, we start from 0. We also in the paper show robustness starting from steady state. We utilize the first 5 years of data to accumulate this series, and then we utilize data as of 2015 onwards for structural estimation. As you can see, there is a very high rise of AI jobs as of 2015 in this data. Finally, we need wages. How do we measure wages? We use a very novel data set. To my knowledge, they have never given their data to researchers, and this data is the pay scale data. This is a crowdsource-based salary data where essentially people fill in these really detailed surveys about their current job position, location, skills required. And in exchange, they give this very, very detailed mapping of how their job relates. So should I learn Python or should I learn Stata in order to get a $2,000 premium on my salary? In renegotiating my salary, how does my role benchmark to other roles in my region? And so people are really incentivized to tell the truth in here because they're going to get a good assessment and nobody else sees this assessment. The business model of this company is that then they aggregate this data and they sell it to firms so that they can be more competitive when they go themselves to hiring in the job market. We utilize a similar method to that utilized in job postings to identify salaries of the three categories of workers utilizing this field of what are the key skills required in your job. And what we find is that indeed AI analysts are in general paid more than either data managers or old tech analysts. What we do is structurally estimate our model. In our structural estimation, as I mentioned earlier, we have the 4 first-order conditions for every firm for every time period. That leads us to roughly 33,000 different conditions. We use nonlinear least square for the estimation, and in each iteration, we use those averages, as I told you prior, to estimate these total factor productivities for time and firm specific. What do we find? Well, the key result of our paper is that this does look like a structural change, not an incremental change. What we find is that the exponent on that data exponent for the old tech or AI technologies, it changes by or 5, by 5%, essentially, it's lower by 5%. To put that into context, this, and this is conservative with a data association rate of 3%. To put that in context, that is within the bounds of the change that was measured using similar methods for the Industrial Revolution. Now, what that means is that we're becoming significantly more productive in analyzing large data sets. That also means that the labor income share actually fell from 18% to 13%. So the owner of the data is getting a bigger share of the pie rather than the workers. That can mean the workers are losing it here, or it can mean that the pie is becoming much larger. So even if workers are getting a smaller percent, they're not necessarily worse off. So this goes to another very big important question that we're after. Are machines gonna take over our jobs? Now, before I go, well, let me answer that. What we find is that just by observing in the data, we don't find that that's the case. Actually, the pie is becoming so much larger, so much more data is being collected and analyzed, that actually hiring has gone up, and particularly has gone up for both AI and tech analysts. Why would that be the case, and what is pinning this down? What is really pinning this down, the difference in exponents, is actually a covariance between the amount of data I have and the amount of analysts I hire at every given time. That goes exactly back to my initial example. If I have the technology that allows me to leverage data more, I'm going to hire more people to utilize the technology, but that is also going to give me an incentive to collect even more data. And so these two things bounce back and forth, which is why it's important to have a structural approach to this problem, because of course these two quantities are endogenous. Now, another nice feature of our data and of our approach is that, as you remember, we estimate this value function for each firm. So what is the value that they can extract from this data? Well, we actually can go back, and through a value function iteration, we can back out the actual value of data. And what we find is that in the aggregate, the value of data in this industry has gone up by 25% in 4 years, from $320 billion to $400 billion. Now, how can we express this in dollars? Simple. Our quantity is salaries. Salaries are paid in dollars. And so the value of data that comes out from our estimation is exactly in dollar terms, like we'd like to see it. What is driving this higher value of data? Larger stock of data, higher cumulative value of data. We have more firms coming in here. Firms that are hiring in AI that have this larger incentive to collect more data. More data, if I accumulate all these up, higher cumulative value. Also, second, as I've shown you, the size of the pie is becoming larger. So I am actually hiring more workers of both types. What it does, I have more analysts. More analysts can draw more insights from data. The value of that data goes up. Third, we measure those productivity parameters. Aside from the firm-level productivity parameters that, as we would expect, have a large heterogeneity, we also have these time series parameters. And what you see here is that we're becoming more productive as using these technologies, and particularly the shift is particularly great for the AI technology. One last thing that I want to point out is that actually this goes back to that non-rivalry of data. Here, both AI and all tech workers are going up. I'm JP Morgan. I collected a bunch of data, and I have an incentive to collect even more because it's not a cost center. Now I have this new technology that allows me to extract value from it. But now the data is in my database. So my old tech team, even if they're less productive at analyzing it, they're also going to hire more. There is a complementarity there because of the non-rivalry of data. So I think I'm out of time, so allow me to conclude. What we do in this paper is we infer how much data each firm has from data management hiring. We then infer how much diminishing returns there are by asking what exponent would make their hiring patterns closest to optimal. The magnitudes we find are very comparable to those of the Industrial Revolution. And so we really think that this is a structural change and is broadly important at an economic level. Change for diminishing returns matters for the value of data as an asset, and that of course matters for inequality from size, competition, and all sorts of other corollary questions that we might want to ask from here. Okay, thanks a lot.
All right, thank you so much for having me and for inviting me to discuss this paper. I've known this paper for quite some time and I'm a really big fan. So it's a really exciting opportunity to be discussing it here. And I guess my first live conference since summer, which was the only one since the start of COVID. So it's been a while. All right, so let me just really briefly summarize the paper, which Simona, of course, did a really good job presenting. So I don't think we need to spend much time on it, and then give some of my thoughts. So this paper addresses a pretty big question, which is how do these new technologies related to artificial intelligence, machine learning, big data concepts affect the production function for firms? And then what does that mean in terms of labor share, overall income, and potential displacement of jobs? How does the paper actually model production of knowledge using these new technologies as well as old technologies? They use a standard Cobb-Douglas framework with two inputs, labor and data. Is the mic too scratchy? I can try.
If I put it too far away, it's going to be not going to pick up. I can try this
one. All right, let's see if this works better. All right, so back to modeling knowledge production with old technology as well as new technology. We have a standard Cobb-Douglas framework with two inputs, labor and data. So instead of capital, the input is data to produce knowledge. And the two different technologies, AI technology, which broadly encompasses all of these new techniques such as machine learning, and old technology, which encompasses kind of standard techniques like running regressions, produce knowledge with different productivity parameters, both different time-varying productivity as well as different firm-specific productivity, and also different elasticities to labor versus data. So this is the key kind of difference between the new technologies and the old technologies, just the parameters in the production function. The data asset itself is also produced from labor, but from labor of so-called data management workers. So the key kind of empirical measures that the paper brings to the table to actually estimate this model structurally consist of the labor stock. So the stock of employees with skills in the new technologies like AI, with skills in the old technologies, standard analysis, and with skills in data management. The employees with skills in data management are key for estimating the actual stock of data. So we don't get to observe firms sort of amounts of data that firms hold, but the quantity of data-related workers who are there to kind of curate that data is a good proxy for the data stock of the firm. And finally, the paper also uses wages from this novel data set pay scale to quantify this. And the main results within at least the asset management industry to date are that the income share going to labor has declined with new technologies. So capital owners, which in this setting is data owners, are getting a higher fraction of the pie, but the overall pie is also growing quite quickly, so that the kind of productivity of labor and the quantity of labor are actually increasing. Jobs are not being displaced by new technologies. And there is a quite sizable increase in the value of the data asset itself, about 25% over the course of only 3 years. So at the high level, I think this paper is really creative and very clever. Conceptually, it's an important topical question, both ex ante as well as ex post. Seeing some of the magnitudes of these results clearly indicates that we do want to know these answers sooner rather than later. I think the model is quite cleverly done. It's conceptually clean, maps straightforward to the types of ways that we are used to thinking about production functions, which is useful. And there is a really careful consideration of the assumptions of the model in the paper, which I really appreciate. The empirics make really clever use of the job postings data. I especially liked this idea of measuring data stock using data workers. That's very clever and gets around a big limitation of the data of not being able to actually observe data assets. And again, there's careful consideration of potential issues empirically, such as, for example, whether the job postings are actually filled. So the paper does an amazing job addressing. So where I'm going to focus my kind of comments during the discussion is just thinking a little bit further about this interpretation and management and what exactly goes on in the knowledge production at the firm and what kinds of workers are there, who's doing what. So the idea of the paper is trying to measure is summarized in the very first sentence of the paper. It's sort of broad new technology like machine learning, artificial intelligence, or big data that are all referring to these new technologies that will reduce the role of human labor and human judgment in producing useful knowledge. So where does this innovation actually fit into the production process? Simona has put up this picture during the slides, sort of the key picture illustration of the model, where we have raw unstructured data that gets sort of cleaned up, structured, stored. That makes the structured data, and then that structured data gets analyzed. So for any of us doing kind of empirical work in sort of fintech related things, this is a very familiar picture, right? We get the data, we have to actually make something useful out of the data, and then we can run the analysis. And where Simona and Laura envision the different workers coming in is the data management workers are going to be the proxy for our stock of structured data. So they're going to come in that first production process, the processing phase. And then the analysts, whether the traditional quant analysts or the data scientists, are going to come in the second part of the process using either the old technology or the new technology. And that's a really intuitive way of modeling it. And I think it's excellent. My only kind of uncertainty is where exactly has the innovation from big data technologies actually fit? So using state-of-the-art sort of finance research, where are some of the innovations in our work? So let's take Simona's excellent papers. So in the current paper, what I would say is kind of the processing phase would be the stemming of the burning glass, kind of job postings, the processing, the identification of dictionaries, search for those words, and then merging the data sets. And then the analysis is estimating the model parameters, the structural estimation. And I would say it's the second part is the part that economists have done probably for longer, working with unstructured text data and job postings, something that economists have started doing much more recently. Looking at kind of, I guess, better examples of Simona's other papers, where she uses kind of random forests to categorize mutual funds, and then kind of hypothesis testing on top of that, or using k-means to group mutual funds into sort of similar groups, and then testing whether the ones that are in kind of within groups are more similar than ones that are across groups, and then kind of how the investors react. The new methods, the machine learning methods, tend to fit into that earlier part of the process. And same goes for kind of my papers that use machine learning techniques. It's usually used to structure the data, that's where it's really important, and then running the analysis we could do using sort of standard OLS, if we just hypothesis testing, we could do structural estimation, or we could use AI there as well, but it's maybe a little bit less sort of critical to use these big data tools. Whereas critical is kind of where we actually need to organize the data. Looking at some of those job postings, which I hope would kind of clarify where exactly the really important machine learning techniques come in, it was really instructive. In some sense, it also highlighted some potential other differences. So again, these are only examples, and like one example from each category. I'm sure there are better examples. But just looking at these, what I see in the kind of data management job posting is that it's a software engineering position. It's a very highly technical position. And there is a lot of emphasis on data size. So it's talking about scaling and working with vast data analysis, capturing, processing massive amounts of data. So there's a lot of emphasis on actually being able to deal with the kind of modern data sets that are much larger than our traditional data sets. Not kind of explicitly talking about machine learning related skills, but this is probably a job where those kinds of technical skills will come in useful. The old tech job is a very broad one. So it's kind of a traditional quant modeling job that would prefer an advanced degree in a hard science, such as computer science or math, coding skills, as well as sort of statistical skills and linear algebra. So there's no kind of emphasis specifically on machine learning. There's emphasis on math, but equal emphasis on computer science. And then the kinds of general skills, statistics and linear algebra, that are sort of prerequisites for doing good machine learning. So if I were, and I'm obviously not, I cannot really speak for them, but if I were a PhD in machine learning rather than a PhD in economics, I'm not sure whether I would apply for what comes next, the data scientist job or this job here. This job seems like actually a pretty good fit for somebody with a PhD in computer science, including potentially machine learning. The data science job does mention more specifically machine learning right at the start. It mentioned machine learning hand in hand with data-driven business intelligence, which does seem to be a term in kind of our MBA teaching of data science techniques. It does kind of talk about sort of joining, enriching, transforming data sets, creating novel measures of economic activity. And then there's quite a bit of more kind of soft language around it. So creating opportunities. We're looking for somebody highly creative and motivated. The role as a lead data scientist. So there was explicit mention of machine learning, but it might also be a significantly less technical job, either the data management job or the traditional data, or the job that got classified as a traditional data analyst. There's no explicit requirement to be able to handle large data sets, because I guess by the time that the data come to them, it's actually pretty manageable. Now, where kind of I'm going with this is, it's not a problem for the paper's theory or the main message. It might have some implications for the actual estimates in terms of where we classify which job and kind of where the salaries fall. So possibly the jobs that focus more on structuring the data rather than just warehousing and sourcing the data might fit better with the kind of data analyst jobs rather than the data management job. But these are pretty kind of minor sort of adjustments that maybe you want to make. I want to say that I did take a look at the entire list of keywords, and those I think were really good. So in general, I think the dictionaries are capturing the kind of distinction that the paper wants to capture. A couple of sort of potentially useful suggestions in terms of further kind of confirming that the differentiation of workers is what we want it to be. I think it would be interesting to look at the distribution of wages for each of the groups. So as an example, if it is the case, the data management includes kind of heterogeneous types where some of them are just sort of literally database admins and others are doing high-level machine learning to structure the data, we're going to see that in the distribution. The distribution might be bimodal with like a noticeable tail of wages at the right end. That might indicate that we want to move those workers out of the data management category. It might also be useful to look at the levels of seniority, just to confirm that they're roughly equal. So in the examples, there was a kind of lead data scientists versus just a standard software engineer. Possibly MBA kind of people would be more likely to go to that data scientist job. So just confirming that on average, the seniority levels are equal. And then also taking a look at some of the other skills. And for this, we can just use burning glass skill clusters, or otherwise just confirming that things like social skills, communication skills are roughly equal across at least the AI workers and the old tech analysis workers. I think that would be useful as well to confirm that it's not other soft skills that are potentially driving some of those shifts and really about the way of analyzing data. A couple of just points on the job postings measure itself. I think that the discussion of accounting for potentially unfilled jobs is excellent. That is really thoughtfully done. I really appreciate the creative way that sort of assuaged taking a look at sort of what are the filling rates from BLS in general. So I think it would be useful to have two other things that are equal, sort of similarly addressed and that might happen with the job postings. One is that some job postings might actually be from multiple lines. So when we make job postings for assistant professors, if we're looking to hire 2 or 3, we're not necessarily going to have different lines unless we're looking at like very specific subfields. So we might just make one job posting, then end up hiring 2 people. So similar things go on, of course, in these companies where we might make a single job posting for a software engineer. We're actually looking to hire a dozen software engineers. And once hired, that's when they get allocated to teams, some of them working on more machine learning stuff and some on more basic things. This is less of an issue with more senior positions, potentially more of an issue with more junior positions. So again, we can do the kind of analysis that Simona and Laura are already doing for job filling rates for potential or kind of likely job multiples rates. And the other thing is whether hiring through recruiters is a potential concern. This is more common in industries like tech and finance than in other industries. And indeed, when we compare job postings against actual employee resumes, we do see more discrepancies in sort of industries like tech and finance, where we might see people joining in resumes, but sort of no job postings made in Burning Glass. That could be an indication of just hiring through recruiters. So again, possibly thinking about this can be alleviated with kind of more international hiring, where job posting of some sort is mandatory, or potentially other kind of heterogeneous aspects that would help confirm that this is not a big issue for the data. All right, I'm going to skip the minor comments and models assumptions as I'm out of time. And to wrap up, it's a really enjoyable paper, and the question is very important. The approach is really creative, both kind of in terms of the modeling as well as the measurement, and especially measurement of the data stock, which I really liked. Yeah, I think it's the results sort of speak for themselves. They're pretty large and meaningful, especially in context of previous technological revolutions, and knowing that we're still pretty early on in this sort of big data revolution. So just a couple of suggestions going forward on kind of clarifying some of the measure and interpretation. And I would recommend anybody who hasn't read this paper to definitely take a look. Thank you.